In this lecture, we're going to look at how to implement a GAN code. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. So at the top we have all our usual imports. We've also imported the save image function from Torch Vision, which is a useful utility for saving an entire batch of images to a single image file. This will let us check how our model progresses over each iteration. Next, we define a set of transformations to perform on the data. Remember that researchers have found that using pixel values in the range -1 to +1 tends to work better. So this code might seem strange at first, but if you check the calculation, you can verify that it works. First, remember that the 2 tensor transformation already scales the image to be between 0 and 1. So if we take 1, subtract a mean of 0.5, and divide by a standard deviation of 0.5, we get 0.5 divided by 0.5, which is 1. If we take 0, subtract a mean of 0.5, and divide by a standard deviation of 0.5, we'll get minus 0.5 divided by 0.5, which is -1. Therefore, we map 1 to 1 and 0 to -1, so this works. Next, we load in the MNIST trained dataset from Torch Vision. You've seen this before. Next, we create a data loader from our dataset. Next, we create our discriminator network. So this is an ANN with layer sizes 784, 512, 256, and 1, and with leaky ReLU activations. Next, we create our generator network. This is an ANN with input dimension 100 and hidden dimensions 256, 512, 1024, and 784. Notice how we've also added a batch norm after each leaky ReLU, and that the neural network ends with a TANH activation, which maps the output values to be between -1 and +1. Next, we set the device to be the GPU, and we move both the discriminator and generator to the GPU. Next, we create our loss and optimizers. For the loss, we can use the binary cross entropy for both cases. The only thing that changes is the label. For the optimizers, we make sure to pass in only the parameters for that specific network. So the D optimizer only optimizes the parameters in the D model, and the G optimizer only optimizes the parameters in the G model. Next, we have a convenience function for scaling images back from -1 +1 to 0, 1. This is useful for plotting and saving and so forth. Next, we create a directory to store the images generated during training. It's called GAN images. Next, we have the training area. So this will be slightly more complex than the code preparation section, since I left out a few minor details. But hopefully you understand the main idea, and so these minor details are just that, minor. So to start, we're going to create one-dimensional arrays just containing 1s and 0s. These will be used as targets during training. The targets are constant values, so instantiating these inside the loop would be wasteful. Next, we create 2 lists to store the losses for the generator and discriminator. Next, we enter a loop that will go for 200 epochs, and inside that loop, we have another loop to go over the data loader. Notice we ignore the targets by using an underscore, since they are not used. Inside the loop, the first thing we do is get n, the batch size. Remember that since the batch size may not divide evenly into the total number of samples, the actual batch size may not be equal to the specified batch size. Next, we take the inputs and flatten them into an n by d matrix and move it to the GPU. And now that we have n, which is the current batch size, we can also index the ones array and the zeros array to get the correct size targets. Next, we have the train discriminator block. The first thing we do is get the loss for the real images. So we pass the inputs through the D model and call that real outputs. Then we pass real outputs into our criterion with ones as the target. We'll call this D-loss real. Next, we calculate the loss for the fake images. So we start by generating some noise, which goes in a matrix of size n by 100. We move that to the GPU. Next, we create our fake images by passing this noise through the generator. Next, we pass the fake images into the discriminator and we get the fake outputs. We pass fake outputs into our criterion with zeros as the target. We'll call this loss D-loss fake. Next, we combine the losses by taking the average. Then we zero the gradients in both optimizers. Then we call dloss.backward and then doptimizer.step to do one step of gradient descent on the discriminator. Next, we have the train generator block. As mentioned, it's been found that training the generator more than once for each iteration is useful. So we do a for loop that goes twice. Inside the loop, we generate some random noise of size n by 100 and move that to the GPU. Next, we pass this to the G model to get a set of fake images. Next, we pass the fake images through the D model to get a set of fake outputs. Next, we pass the outputs through the criterion, this time using ones as the targets. This is because we would like the discriminator to think these are real. Next, we do a gradient descent step. First, we zero the gradients. Then we call gloss.backward, and then we call goptimizer.step. And remember that even though the outputs that go into the loss function are outputs from the discriminator, we are running goptimizer, which only knows about the G model's parameters. So only the G model's parameters are updated. Finally, we save the losses to our list of losses. We print the epoch number and the losses. And then, at the end of each epoch, we save the fake images that were last generated using the save image function that we imported earlier. Note that before we save the images, we have to scale them back to the correct range using the scale image function. Okay, so let's check out the loss per iteration. So as promised, it's not the nice downward converging pattern that you're used to. Okay, so let's look at the images we generated. So here are the fake images after epoch 1. We can see that at this point, they are already starting to resemble the MNIST dataset. After epoch 50, it pretty much looks like MNIST. After epoch 100, it looks even more like MNIST. After epoch 150, it still looks like MNIST. Maybe even a little better. And after epoch 200, it still looks like MNIST. So, as you can see, the results are pretty much what we expect. At the beginning, we didn't see anything at all, and by the end, it looks pretty much like MNIST. The generator learns to generate real-looking digits quickly, so there's an aspect of diminishing returns here. After the first third of the way through, things already look pretty good.